Let's start.
Yes, please.
Oh, okay, thank you. So, good morning, everyone. I'm Zhichen Zhang from Tianjin University. Welcome to our series of virtual academic seminars to celebrate the launch of SmartMat. SmartMat is co-launched by Winnie and Tianjin University. I'm one of the social editors of SmartMat. The editors-in-chief of SmartMat are Professor Wenping Hu from Tianjin University and Professor Hua Zhang from City University of Hong Kong. Now, SmartMat has been indexed by ESCI with a first impact factor of 20.4. SmartMat has also been selected as Zone 1 in Chinese Academic Sciences Division. Welcome to submit your work to SmartMat. Today, Dr. Annie Electrocatalytic from Major University will give the presentation. Now, I'd like to briefly introduce Dr. Electrocatalytic first. Just wait. Okay. Dr. Annie Electrocatalytic received his bachelor and master degree in chemical engineering from Amical Kabir University of Technology in Iran, with a major in molecular dynamics simulations. He completed his PhD degree in 2014 in the Department of Chemical Engineering at Polytechnic Montreal. During this period, he investigated non-noble electrocatalysis for the oxygen reduction reaction in PEM fuel cells. He was trained as a postdoctoral fellow at the University of Montreal, Duke University, and as an FRQNT postdoctoral fellow at the University of Toronto. He joined the Department of Chemical Engineering at Major University as an assistant professor in January 2019. Dr. Electrocatalytic is a Canada Research Chair in Electrocatalysis for renewable energy production and conversion. And his research team is focused on developing catalytic and functional materials for green energy technologies with a particular interest in carbon dioxide conversion, nitrate reduction, and biomass upgrading systems. Dr. Electrocatalytic has been invited to present in 15 national and international conferences and has published more than 50 scientific articles, which have been referred to more than 8,000 times based on Google Scholar. Today, Dr. Annie Electrocatalytic will give a talk about engineering extremely small nanoparticles with high electrocatalytic performance for CO2 conversion. Let's welcome Dr. Electrocatalytic, please. Thank you. So now I will stop sharing the slides. Okay, please share. Thank you.
Great. Thank you so much, Professor Cheng. I appreciate this opportunity. And I'm happy to be here with you and with your audience. It's a great honor to present my research. I hope I can speak about something interesting and people can enjoy and learn from the presentation. So, all right, I hope you can see my screen. As you mentioned, I'm going to talk about engineering extremely small nanoparticles with high electrocatalytic performance for CO2 conversion. You gave a very comprehensive introduction about me. I don't really need to talk about myself anymore, but my research lab, which is called Electrocatalysis Lab, is at McGill University Department of Chemical Engineering. So with that, to just briefly introduce our research lab and mention what we are working on, I would say our lab, which is called Electrocatalysis Lab, is focused on electrochemical system, working with these electrolyzer and to convert some of the raw chemicals with a few of them are also considered as waste, such as carbon dioxide or bio waste and nitrite from the wastewater, and also always having the water and nitrogen in our system to produce some value-added chemicals. And these chemicals include hydrocarbons, fuels, or valuable biomass, also including ammonia, urea, and green hydrogen. So a lot of our focus recently is on hydrogen and also biomass valorization. But today I'm mostly focused on carbon dioxide conversion to hydrocarbons and fuels. If I have time, I will also talk a little bit about the bio-waste conversion. So I assume you have audience with a very broad disciplines. So please forgive me for giving a little bit context about my research and why we do electrochemical conversion, CO2 conversion. So what's going on now everywhere around the world is we utilize fossil fuels to feed the humankind activities, and after that we just release the CO2 into the atmosphere, and that's what we are now. But then if we be able to somehow just capture and convert the CO2 into green fuels or in a sustainable way, and again, just within a circular system, feed the human activities, then we can have a more sustainable society, more sustainable environment, and even economy. But of course, this needs to have access to renewable sources of energy, including solar cells or solar energy, wind energy, and hydro energy, which in Canada, fortunately, we have a lot of green electricity, including the hydroelectricity. So then what we do, our research basically makes sense. Again, to provide a little bit more context about how these electrochemical reactors work, I should start with perhaps the different types of the electrochemical reactors. Many of you may know already, but again, briefly, I would like to mention that we work with two types of electrochemical setups. One is called H-cell, and the name is coming basically from the shape of the electrochemical setup, which looks like the letter H. And then the other one is the flow cell system that I'm going to talk about in a second. So in both of these systems, the CO2 is the reactant, and then we produce a bunch of different products. And we always have two types of reaction ongoing. One is the oxidation reaction, which happens at the anode side, and then one reduction reaction, which happens at the cathode side. Our CO2 reduction reaction happening in the cathode side. And as you see, you can convert CO2 to different products, different hydrocarbons, either oxygenated or non-oxygenated one. But then this reaction needs to be coupled with the anodic reaction, with oxidation reaction, and the oxygen evolution reaction, which comes from the water electrolysis, is the most common one, which is used in so many research labs. If, again, I have time, I will a little bit talk about that one too, but the focus today is on the CO2 reduction reaction. So in H-cell, as you may notice here, we have a solution, which is our electrolyte, to provide the conductive, ionic conductive media. And then we apply the electrical circuit outside. Then the CO2 needs to be purged inside the electrolyte. And you see here a real actual picture of our setup. So the CO2 needs to be purged inside the electrolyte. And then we will have a saturated electrolyte. Then the CO2 needs to diffuse from the bulk of the solution to the surface of the electrode where the reaction is happening. So at the working electrode, we have the reaction ongoing. And there are some limitations associated with that. First of all, you cannot use any types of the electrolyte that you want. For example, if you use alkaline electrolytes such as potassium hydroxide, then the CO2 will react with that. And before being converted to the desired products, it will be converted into carbonate or bicarbonate salts that you don't want it. So you cannot use any types of the electrolyte. And also, the reaction rate is limited by the diffusion rate of the CO2 from the bulk to the surface of the electrolyte. So for these limitations, people started working with the flow cell system, in which we separate the gas, the CO2 gas, from the electrolyte. So here you see that there is a channel, the CO2, which is separated from the electrolyte that we often use, and is our catalyte. And now it can be any types of electrolyte that you want, either from acidic electrolyte to neutral that people were using usually in cell system, all the way to the alkaline electrolytes, such as very saturated potassium hydroxide. But then this catalyst that we have it here needs to be on a support which is porous. And the support needs to let the gas to pass through, reach the surface of the electrode and the surface of the catalyst to be converted. And here you see again a schematic of our system. Usually we use a copper-based catalyst because it's I would say so far the only transition metal catalyst which is able to convert the CO2 into different hydrocarbons. The other metals either produce just CO, carbon monoxide, and also formate or formic acid depending on the electrolyte. But so we use mostly copper-based catalysts, and also for the anode side, if that's the oxygen evolution reaction, we use nickel-based catalysts or platinum-based catalysts. So when we have the reaction, either using the cell or using the flow cell system, then you may produce a bunch of different products as already mentioned here. So you may have the carbon monoxide, you may have formate, you may have methane, ethylene, ethanol, propanol, so many different products. And that can be an opportunity, but at the same time, it could be also a challenge. Why it's opportunity? Because, then you can work with different end users, different industries. Currently I'm working with two different companies. One of them is interested in ethylene. So I can just fine tune my system or change the catalyst for the same reaction, produce ethylene. Another company that I'm working with them actively are interested in formic acid or formate. So I can also use the same setup, same knowledge, same concept to produce formate for them. So this is the opportunity that gives us a huge degree of freedom. But then the challenge is people won't be happy if you give them a mixture of different products. If they are interested in ethylene, they want ethylene with 100% purity. They don't want to see any trace amount of CO because most likely they are going to use that ethylene in a petrochemical processes to produce polyethylene. And then if you have a CO, that CO will poison their catalyst and they don't want it. So with this background now, and also talking about the industry and end user in these processes, so something that comes up is how efficient is our solution, our system. Energy efficiency is one of the top metrics that we are always pursuing to improve it. And after that, the system, the solution that we provide to convert the CO2 and overcome some challenges like global warming and the climate change, the system needs to be also practical. When we say the system needs to be practical, we mean it needs to be able to do this conversion in a very large scale. So that's why the reaction rate or the reaction throughput is also very important. And eventually the system, which is efficient and also is able to work at very high reaction rate, needs to be also stable. You don't want to have a very efficient system which works at very high reaction rate, just work for a few hours or a few days. You want it to work at least for a year or 2 years. So how we can improve these parameters, for the energy efficiency, we need to improve the catalytic selectivity and also catalytic activity. The selectivity means if you are interested in producing ethylene, then just produce ethylene. Don't produce anything else. And we measure it and we kind of evaluate it through the Faraday efficiency parameter that I'm going to talk a little bit more about that. And then the catalytic activity means the energy input to the system, which is translated to the applied voltage in our context. So you want to work with a system which requires the smallest possible applied voltage, but at the same time be very selective to improve the energy efficiency. Of course, you want to work at very high current density and also with a very stable system. So there are different approaches. We take on 3 different approaches in our research lab, either doing some engineering, like in modifying the reaction environment, changing the setup, or optimizing the electrolyte. or developing new selective and active catalysts, which is the topic of our talk today, or even modifying the electrochemical setup overall. So among different products that I just mentioned here, methane is the interest for today. We work on different products. In our lab, we are focused, as I mentioned, on formate, ethylene, ethanol, and also methane. But for today, I'm speaking about methane. The main reason is it's quite challenging to produce, and you don't see too many papers out there, as I said, because it's not easy to produce with a high efficiency and selectivity and at high current density, but also the methane coming from fossil fuel is very cheap. For ethylene, you may be in a position to compete with the market that produce ethylene from the fossil fuel. Same for CO or formate, but for methane is difficult because methane is too cheap coming from the natural gas. Here you see a few top literature reporting, some of the best results for the methane production. And as you see, the highest selectivity, which is presented by the Faraday efficiency, which is the electron selectivity, basically, is around 80%, but that comes with very low current density. And the current density is talking about the reaction rate. So around 20 milliampere is nothing that we can think about industrialization. We often need a couple of 100 milliamperes or above 1 ampere. To just give you an idea, the water electrolysis system works usually at more than 2-3 ampere. So 20 milliampere is almost 3 orders of magnitude smaller than what we are looking for. And then it's also associated with very large applied potential, which means the system is not active. And then if you improve the reaction rate, like almost 1 order of magnitude, then the selectivity decreases. And although in this work, they achieve a very impressive low applied potential too. But if you notice, all of these works are coming in, people are working in neutral electrolyte. And in next slide, I'm going to explain why people just work in neutral electrolyte, not alkyne electrolyte, even though they are using the flow cell system. So this work shows some of the early results done by Hori. His pioneering work published more than 30, no, not more than 30 years, but almost 30 years now, 25 years now, which in fact shows that the selectivity for different products can change based on the potential that we apply to the system. At low potential, we see the hydrogen is the dominant product in terms of the selectivity, but then increasing the potential that we can also increase the applied obtained current density, then we can switch to produce ethylene or methane, but it also depends on the electrolyte that we use. This is represented again in neutral electrolyte, and you see that we can achieve methane, but at very low current density, around 10, 20 milliampere, which is not, again, industrial level. But then if we move on to very higher voltage to further increase the current, but then we realize that the hydrogen picks up and then it becomes the dominant product. So you cannot simply increase the volt potential and increase the current in neutral environment, because then hydrogen becomes the dominant product. But then people use basic environment, and we have a paper here, you can look into that. We describe why in basic environment, then carbon-carbon coupling becomes easier, and then you can produce multi-carbon products such as ethylene much easier in basic environment. And since you are working in basic environment, the electrolyte that you're using is even more conductive, ionic conductive, so you don't really have to apply a very large potential to achieve a high current density. So you can achieve high current density at lower potential in basic environment, but then the problem is, as we described here, since CC coupling is easier, you produce mostly ethylene and you can't produce methane. But our goal is to achieve a high current density most likely at low potential for which we need basic environment, but how we can do it. So looking into literature, you will learn that people are talking about different crystalline facets for copper. And as I said, copper is one of the so far the only transition metal which is able to produce hydrocarbons from CO2 in electrochemical reactions, of course, not thermal catalysis. So people show that if you use copper with 100 facet, crystalline facet, you most likely get a lot of ethylene. And vice versa, if you have copper with single crystal copper with the 111 facet, you most likely get methane, not significant amount of ethylene. And then there are also other works showing the product selectivity relationship with the particle size, for which they demonstrate, for example, by changing the particle size, you may also change the selectivity. But in literature, people work with a very large particles, such as 1 micron or even larger particles, down to very small particles, such as 25 nanometer particle size for copper. So in our lab, we were interested to see what happens if we go further down and utilize very small particles. Then first of all, we had two questions. The first question was that what happens to the particles' crystallinity? Do we have more of 111 at a smaller particle size, or we have more 100, or maybe other facets? So for that, what we did, we started like DFT projects with running a huge amount of computations, and we created particles with different shapes at different sizes. So this was really a massive project. Here you just see the select particle shapes and at different sizes. But for each size, we had multiple, sometimes a couple of tens of different configurations and different shapes, depending on the surface energy and also the facet that we included. So we included 111 facet, 100 facet, 110 facet, and also 211, which is not represented here because it wasn't stable. And after that, at each particle size, we evaluated the excess energy to see which particle shape at that size is the most stable. So what we realized was when the particles are large, then you have a combination of different facets, just 111, 100, and 110. But the 100 facet was the dominant or compared to the 111. So the ratio of 100 to 111 just kept increasing when the particle size was increasing. So here you see the ratio was increasing. But then on the opposite side, when the particle was extremely small, then you don't see 100 or 110 or 211. And the particle is most stable if we have only 111 facets. So this pyramid shape is the smallest particle that we can have with just 19 atoms, for example, and shows the highest stability within this ring. So with that knowledge coming from just pure computation, we tried to synthesize particles with different sizes. We used a sputtering system, different electron beam sputtering systems, or thermal evaporation. And then we synthesized samples with different sizes from 1 nanometer to 200 nanometer, even smaller than 1 nanometer. In fact, in few slides, I'm showing 0.5 nanometer or 5 angstrom particles that we synthesized. And these numbers are, I mean, these values are just nominal sizes, of course. These are not actual. So the actual size is slightly larger. So here you see 1 nanometer particles, and then 2 nanometer, 4 nanometer, and 100 nanometers. So these are the SEM images. It's not very super clear, but I hope you can pick some of the features showing the particles, the small particles. And then when the particle size becomes too large, then it's kind of conformal and you have the copper everywhere. So we utilize the carbon support here, which is the wireless type. And it's the provider is actually a Chinese company, so we always buy it through them. And it's a great support for our research. And then we spotted those copper particles on these carbon support. So EDX, as you see here, shows for example, here you have a lot of copper, smaller and smaller, and it's quite not clear, I would say here, unless otherwise you zoom in on the video, and then you may see some bright dots there. So after synthesizing that, we were interested to know if we have 111 facet or 100 facet, what facet do we have? Our TEM, Dartwell TEM and SAED showed that as we were expecting from the DFT computation, for small particles such as 1 nanometer, you only see 111 facets. While the particle size increases to 100 nanometer, for example, then not only you have the 111 facet, but you also have the 200 or 100 facet. And here you see again, for very small particle, unfortunately, we couldn't go lower in terms of the size. We would love to be able to do it, but our TEM here at McGill are not able to detect particles or smaller than that if for the crystallinity. But obviously, as you see, when the particle size increased, we observed more signals from other facets, kind of proving or supporting what we just mentioned in the previous slides, that you have more 111 here and then more 100 here. So with this knowledge now, so we know when you have extremely small particle, you most likely have a particle with this size. But then when you have a larger particle, such as 100 nanometer size, then you have more 100. Then what happens to the reaction mechanism? People investigated this a lot in literature, including myself. We have so many papers that we always use the SLAB model to do the DFT computation, but not really working on those small particles. I just forgot to also mention that we ran different characterizations too to further investigate the crystallinity, including the XAS, X-ray absorption spectroscopy, both in situ and ex situ, and also the XPS. XPS was just showing that for a small particle like 1 nanometer, we mostly have a copper 2+ because it's easily oxidized. And then XAS, X situ XAS was also proving the same thing. But as soon as we run the experiment and we apply the potential, then all of them go back to the metallic copper, so copper 0. So I just forgot to talk about that. So coming back to the mechanism, as I was saying, we always were using the SLAB model, which means you are using a periodic model in DFT computation. So it represents a large surface area. It doesn't really represent isolated small particle. So this time we said, let's just look into the reaction mechanism following the same path based on the literature and our prior work, but on this pyramid-shaped kind of particles to see what happened. There were a few interesting observations. One of them was the absorption energy for most of the molecules were much stronger on these particles than the slab, than the surface. For example, CO2 often doesn't even absorb or doesn't even come close to the surface. But under the same condition, same like a kind of a solvent model or applied potential, everything similar, then we observe that, interestingly, it can be absorbed on the surface of the small particles. And that was the same case for ethylene or methane. So we observed different absorption energy. But I would say the most interesting part was about the ethylene absorption. So as I said, ethylene was absorbed on the surface strongly so that it doesn't really dissolve from the surface. So this is the interesting part. So we followed the reaction mechanism, different possibility. The highlight here shows the most feasible pathway or energetically most favorable pathway. But then interestingly, we are able to produce ethylene. But then even using these small nanoparticles, but then what happens, ethylene doesn't leave the surface. So the barrier to leave the surface is too much, like 1 electron volt. But then on the other side, if we keep further protonating the ethylene, the energy is not uphill, it's rather downhill, and you can easily expect this step. So once further protonation happens, again, next step is still too difficult to produce methane, to leave the methane or get back to this one. But you can again do another hydrogenation. So you can easily expect that as soon as the ethylene adsorbs on the surface, you can convert it to the adsorbed ethane. But then ethane can leave the surface much easier than ethylene. So here the energy barrier to leave the surface was 1 electron volt that we don't expect to happen easily, even at room temperature. But then for ethane, it was 1/4 of that, like a 20% of that, 0.25 electron volt, which is surmountable. And you can expect that even at room temperature. And if you increase the temperature further, you can help to observe more ethane. But then what happens, I mean, even a more favorable pathway is once you have the ethane, instead of leaving the surface, it can quickly be converted to methane. So either producing 2 methane, dissolved methane, or 1 methane and then another adsorbed methyl group, which can be further converted into methane through another hydrogenation step. So this observation was telling us now that if we use this particle, extremely small particle, we should expect more methane than ethylene. That which is not the case when you use, in fact, the copper spotted on carbon in many papers, including some of my own research papers published previously. And also we expect to observe some ethane. So to further investigate this hypothesis, we were curious about like detecting ethane, because we said ethane is something that we may expect, but not ethylene. And then we calibrated carefully our gas chromatography, and then we observed the ethane peak on extremely small particle, like on 1 nanometer particle or 0.5 nanometer particle. And also by increasing the temperature, we observed that the amount of the ethane that released is also increased for the same reaction condition. Just, I mean, by reaction condition, I mean, same electrolyte, same flow rate for the gas, same temperature, applied potential, same current density. The only difference was we just heated up a little bit the electrolyte, so we got higher temperature, so it enables the ethane to leave the surface much easier. But then there was absolutely no peak on larger particles, like 100 nanometer or 200 nanometer. So kind of supporting our hypothesis that the small particles is able to adsorb ethylene strongly and then be converted to ethane to leave the surface. And then also our Raman spectroscopy, in situ Raman, showed that on a small particles, you have some features demonstrating that there is a CC bond, but on large particle, we didn't see that, simply because on large particle, as soon as the ethylene is generated, it leaves the surface. So you don't have really a high population of the ethylene adsorbed on the surface. But on a small particles here, you see those features showing that the C, and also the CH bond are existent there. So with all this, the most important, or the summary of this work basically is that we synthesize particles with different nominal sizes, starting from 1 nanometer all the way to 200 nanometer. We applied 100 milliampere current density, and then we measured the selectivity. I like this figure a lot because it beautifully shows the trend that we expect. At this size, our result is very consistent with the other literature, showing that the 200 nanometer copper, the spotted copper in alkaline environment, can produce like ethylene with around 40–50% selectivity and no methane. We had other products too, including hydrogen, CO, ethanol, and formic and acetate, but absolutely no methane, not detectable one. And then when we decrease the particle size, you see that the ethylene selectivity decreases, and at very small particle, like a 1 nanometer, you absolutely observe no ethylene. And then methane selectivity just ramps up and you observe more methane, which is very consistent with our DFT computations, showing that if you work in this range, you must have more methane than ethylene. And interestingly, this work is not even in neutral condition. That so far, most, as I said, I mentioned in the, I guess here in this table, all these works are in kind of a neutral or pH around 8 or 9 maximum. But then here we are using 1 molar KOH with a pH of 13, 14. And so are able to produce 80%, around 75, 80% methane with 100 milliampere current density. So we further engineered the electrolyte to achieve higher current density. We also decreased the size even smaller than 1 nanometer. So here you see the results for 0.5 nanometer particles. And the electrolyte is the mix of KOH and also some KCl to just provide enough potassium for the solution. And then we were able to achieve impressively high current density, like work around 1.6 ampere total current for CO2 conversion. But then the partial current density was 1.2 ampere, which is 1 order of magnitude larger the best one that I showed in the table. But we have recently few interesting works also coming from my colleagues and friends lab showing that methane can be achieved at around 500 milliampere. But this one is at least 2 times larger than them, and it's coming with a very high selectivity, around 85% at the optimum condition. And we were able to run the system for around 14 hours. Unfortunately, we are not able to run it further. One reason is the particles are very small, and which makes it quite challenging to run for a very long time. So again, coming back to this table, now using our copper, extremely small copper that we call them nanoclusters, we were able to utilize alkaline environment and is still not producing ethylene. Just a reminder again, the problem with using the pH 14 is that people just promote ethylene production, but we were able to suppress the ethylene completely using this type of catalyst and achieving very high particle efficiency. This one is actually 1200, it's the typo here, larger than 1200 milliampere per square centimeter. And more importantly, after converting the applied potential to the RHA scale and also considering the ohmic resistance, the applied potential versus RHA is less than what we had before. So here, I would like to just thank my students, Mehdi Salehi, a PhD student still working in my lab, and Hassan Al-Mahaini, a master's student who was running the DFT computation. This work is still under review, and hopefully very soon we can you can have access to the paper. I'm going to switch the topic, but it will be very brief, perhaps in 5 minutes or 7 minutes. I can just wrap it up. But the topic is a little bit different. In previous topic, I was focused on the CO2 reduction reaction, which happens in the catalytic side. And as I mentioned, people often just combine this reaction with oxygen evolution reaction. So if you remember, one of the main important metric for us and for commercializing of these kind of processes is the energy efficiency. So here you see the applied potential for the OER is very large, for the oxygen evolution is very large. And the product that you generate here is the oxygen that you don't really want it, because you can produce oxygen through other separation methods much cheaper, much cheaper. So it doesn't really make sense to have this reaction combined with CO2RR if the focus is here on the CO2 reduction reaction. So people say, instead of oxygen, but we need the oxidation reaction. Otherwise, electrochemical system cannot work simply. You need to have both sides, the cathode and the anode. So people say that oxidation of the OH is too difficult, But if you have organic compound, breaking the CH bond is much easier than breaking the OH bond. So organic compound oxidation must be easier, so it requires a smaller potential, such as ethanol oxidation reaction or formic acid oxidation reaction. Or recently, people are focused on hydroxymethyl furfural oxidation reaction, or HMF-OR. And you see here, you start with hydroxymethyl furfural here, and then, here, which has aldehyde group and the alcohol group, and then you convert it to FDCA, which is the furandicarboxylic acid, has two carboxylic acid groups. So we wanted also to try this one and then combine our CO2 reduction reaction with HMF-OR. The first thing was developing an active catalyst for this reaction, and after that combining it within the system to see how much energy you can save and how much you can improve the energy efficiency. So again, just quickly showing you what happens when you start with HMF and you are oxidizing that. You can go all the way through the 6 electron transfer steps to from the carboxylic acid or FDCA. But it can go through different pathways. You may produce HMFCA or DFF, but eventually FFCA and then FDCA. So we developed again, we were working with, again, a small nanoparticles, but this time we were working with nickel. Nickel is very a good catalyst for most of the oxidation reaction. Doesn't really matter water or organic compounds. It's a good start always. It's a good benchmark. But it has also a lot of problems. If you want to use nickel for HMF oxidation reaction, let's say here, once you have the HMF-OR on nickel, then you also start having OER quickly. So there is a big overlap between the OER and HMF-OR. So you need to make it more selective for just HMF-OR. So we started working with the nickel phosphorus. So we synthesized that, but then we just kind of leached out, but basically reduced the NIP to just nickel on the surface. And we obtained this core shell structure. At the surface, you have the nickel. In the core, you have a still nickel and phosphorus. And we show that through different XPS analysis or even just EDX and SCM analysis to see how this amorphous structure is generated. We got, in fact, a very interesting results, very high selectivity, very high current density. The problem is whenever we use metallic compound, we need to work in alkaline environment. Otherwise, the HMF doesn't get activated. And then the reaction selectivity and activity is not great. So you have to work with alkaline electrolytes such as 1 molar KOH to initiate the reaction. And you see, these days, you see a lot of papers for the HMF. They are utilizing like a 1 molar KOH, for example. But most of them, they don't even discuss that. But what we observe in the lab is just putting HMF inside the 1 molar KOH and just waiting. No applied potential, nothing. Just basically put the HMF inside the 1 molar KOH and wait. In 1 hour, you see what happens to the HMF. So it starts just being degraded, which you don't want. So that's a challenge. So you don't want to really work with the HMF in alkaline environment. We have a few papers on that. We also work in alkaline environment, but this is the challenge that I would like to mention. So we need to be careful about it. So what we can do, people are using molecular catalysts like a TEMPO, which has this structure as the mediator or as the catalyst. But these type of catalysts, molecular catalysts, needs to be dissolved inside the electrolyte. You still have the electrode, solid electrode, can be carbon paper, carbon, glassy carbon rod, or the carbon felt, different sorts of conductive material. But then the TEMPO, for example, is dissolved in the solution. So these catalysts works perfectly. You can convert the HMF using these type of catalysts at very low pH, such as pH 7, 8 even. So you don't have any more degradation problem. The challenge is the catalyst is within the system. So you need to separate it after the reaction. So the separation after the reaction is the issue. So it increases the the cost basically and decreases the efficiency. So if we have this, then we were thinking, what if we just immobilize tempo on the surface of the electrode, so we benefit from using low pH, but at the same time not having the issue of tempo dissolving the solution. So you can have your catalyst always there. Immobilizing tempo itself is not really an easy job. So we went through a little bit complicated chemistry procedure, but eventually we were able to functionalize the tempo like this one. And then through the electrografting procedure, we immobilize that on the surface of different supports such as carbon felt and graphite and also glassy carbon rock. And the electrografting system is quite simple. You just run a CV for a few cycles. You need to optimize it, and to optimize it, we were using EIS or frequency response analyzer to understand how many cycles we require to have the optimum coverage, surface coverage of the tempo. So long story short, we also went through some sorts of characterization, for example, XPS or some pure electrochemical theory to confirm that our tempo is immobilized on the surface. And after that, we utilized it. As you see here, we were able to work under different pH from pH 8, 9, 10, 11, 12. So these are just shifted to show them better. Otherwise, they all are at the same potential range. So you see that, of course, by increasing the pH, the current density increases, but then you also promote further oxygen evolution reaction. So to avoid that, we were utilizing the pH 8, and then we were applying different potentials. So the potential could start from 1.6, go all the way to 2, but then the larger potential again promotes the oxygen evolution reaction, and that's why you don't see the HMF products efficiency or sorry, the selectivity to be adds up to 100% because the rest is just oxygen. So for us in this case, 1.6 volt was the optimum voltage. But as you see, applying that voltage for a short time, like 1 hour, as you see here, is not good enough because although you are converting the HMF to different products, as we mentioned, HMFCA, DFF, FFCA, and also FDCA. But if the target product is FDCA, 1 hour is not enough. You need to work with that system for a longer period. So that's also a challenge coming with this system. But it's quite selective, and also it doesn't really need alkaline environment. So just a summary. We showed that metal-based catalysts require a high pH for HMF oxidation reaction, but HMF degrades at high pH, such as greater than 30. Then, on the other hand, molecular catalysts, not the metal-based catalysts, such as tempo, they can convert HMF to FEC at lower pH, but the post-reaction separation and catalyst loss over time are major concerns. So you don't want to lose your catalyst every time that you're running the system. So what we did, we immobilized tempo, and we were able to convert HMF to FDC at lower pH, which is quite promising. And this is where we started. And electrografting is the procedure that we followed. But the reaction is still low, and we know that we need to work on it, how to increase the let's say, turnover frequency on the immobilized catalyst. So immobilization of on material with high surface area, such as carbon felt, can resolve this. So if you use a high surface area carbon felt, then you can run the reaction at a faster rate and then achieve higher conversion. So at the end, I would like to also thanks my students, Kevin, a master's student in my lab, and my collaborator, Maryam Abdinejad, who is a postdoc at MIT currently. And I also would like to acknowledge the support that I received from different agencies, Complete Canada for running the DF competition, NSERC, and CFI and Canada Research Chair, and FR20 for supporting my research. So with that, I end my talk here. I guess I was a bit long. It's almost 50 minutes. And I would be happy to take questions if you have any. Not sure if should I stop my sharing my presentation here or I keep it like that.
Hi, Dr. Electrocatalytic.
You can call me
Thanks.
Alan, I guess.
Thanks again for your wonderful talk. Yeah, very interesting work. Especially for these small nanoparticles, control the size and control the selectivity towards C1, C2 products, and also for some biomass upgrading, for example, HMF oxidation reaction and other biomass upgrading electro oxidation reactions. Thank you. Yeah, very interesting work. So now our staff have collected some questions from different live platforms such as Bilibili, Baidu Live, and other live platforms. So maybe I will ask the questions on behalf of the audience. Also, if you have any questions, you can communicate with Dr. Saito Kandani. Now, I check the number of the audience in Bilibili live platforms. Now, the number of the audience is more than, let me check, more than 8,000, 5,800. So
Yeah,
many.
that's very impressive. I
Yeah.
never talked in front of that many people, so I'm so
Yeah,
glad you have that many audience.
yeah. I also share the link to you by email. Yeah, you can check it. So many. Only this live platform. Yeah. So I have one question. Yeah. First I will ask you one question. Very interesting work actually. Just now you mentioned maybe slide 15, page 15. You mentioned just control the size. Small size will facilitate the formation of methane. Yeah, you mentioned in this figure. Yeah, yeah. Small size nanoparticles. The main product is methane, and large size, big size, ethylene. Yeah. So for big size, actually, is good for CC company. Yes. So do
Yes.
you think the reason I think is related to the size or the facet? Why big size is will facilitate the formation of ethylene, CC company, to form the ethylene? Yeah. Thank
Yeah,
you.
this is a very interesting question, and there might be multiple reasons for that. I mean, just being focused on what we did here to justify why larger particles can produce ethylene or CC or the CC coupling is easier. I can refer to this one. As I said, when you increase the particle size, although this is not actually even in the order of 200 nanometer, but you can see the 100 facet to 111 ratio increases. So you have more 100 facet. So an enlarged particle size that we obtain through a sputtering, let's say if you sputter 100 nanometer particle size, then you have a multicrystalline or polycrystalline copper. So you have those 100 facet. And then in different works, people showed that when you have 100 facet, then CC coupling is easier. So this can be one reason. And also on the other side, when you have a very small particle, there is no chance for those coupling to happen. So that's my answer from this angle. But I guess which is quite consistent with what people observe also in their work. Just a large particle size, they observe more ethylene.
So my another question, just also related to this question. So you mentioned 100 facet of covalent structures, small nanoparticles, will
Yes.
facilitate the formation of ethylene CC complex. So why you don't just synthesize copper nanocubes, expose all 100 facet actually? Yeah.
100 facet, you said?
Yeah. For
So
copper
yeah,
nanocubes. Yeah.
absolutely. So this is one way to have kind of either single crystal metal, then to further investigate if that's actually super selective towards ethylene or not. But earlier I mentioned we were interested in methane for some reasons.
Oh.
green methane, for example, production in Canada. But then we were also interested to investigate in that small size that people haven't really explored that much, at least for the CO2 reduction reaction. I've been working on CO2 projects, but the smallest particle size that we were using were around like a 10, 15 nanometer. And even for those 20 nanometer, even for those we were further doing electrodeposition to increase the thickness of the sample. So I was thinking, okay, nobody actually knows what we should get from copper at that small size. So let's just try it. And then we observe quite different products than what we were expecting at larger scale.
Okay. Thank you. Thanks for your detailed response. So I think for especially for the mixed phases for the small nanoparticles or even bigger size, actually they are just a boundary, between
Yes.
different facet, the
Yes.
boundary. I think maybe for the mixed facet, we just maybe we facilitate the formation of the CC company, because maybe just like you also mentioned for the especially for Car C2 products, for ethanol, ethylene, refer to CC company.
Yes.
For one facet is CO and another facet or another CO, just CC company, maybe asymmetrical CC company or massive or symmetrical CC company, so in this way, the boundary is very important to just pollute the formation of the CC company for this
Exactly.
process. Maybe.
Yeah, no,
So
I agree with you. And I guess both those grain boundaries are important. And
yeah.
most likely the reaction happens mostly in those boundaries. And if you have larger particles, then you provide more grain boundaries. And then also the CO, let's say assume that the CO is the reaction intermediate, the critical reaction intermediate for CC coupling, and then you provide
Yeah.
larger opportunity.
Yeah.
In fact, that was very, very early hypothesis that we had. We were saying that, like, let's say if we use a small particle, there's no chance for multiple CO to be there to combine and produce ethylene. So our hypothesis started from there, very original, like a few years ago. But then later on, we realized it's not just about the particle itself, the size, it's also the shape of the particle, which is important. And we realized if we have a small particle, most likely we have something like this, if we want it to be stable.
Yes. Yeah, well, maybe already published paper for cuprous oxide.
Yes.
They mentioned, they also mentioned this mechanism. They proposed this mechanism on the boundary. We have facilitated the CC company symmetrical. Maybe one facet COH or CHO, another facet CO. Asymmetrical CC company will happen. And we're not sure about copper. Copper nanostructures, especially for these nanoparticles, small nanoparticles. I'm not sure, especially for the mixed phases. So very interesting work.
Thank you.
So our staff also collected some questions from the live platforms. So I will ask questions on behalf of the audience. Let me see. Let me check it. Oh, I just checked the words. Maybe he or she means. Just
Hello,
mention, you mentioned.
hello,
Oh, okay.
Professor Zhang. Can I ask a question first? Hello,
Okay.
Professor. Okay.
Please.
Yeah.
Good.
Hi, Professor. Thank you for your wonderful talk. I'm from the Nanjing University of Science and Technology. I have a similar question with Professor Zhang Zhicheng's questions. But I'm more interested in about the methane production. So I'm just wondering about why the small particles is more special for the methane production. So could you please give a more explanation on the reason? So why the small particle is special?
Yeah, okay. So at the beginning, I should mention that this is also new to us. And then what I'm saying might be only one reason, one possible reason. I cannot exclude any other possibilities. But with that, here we showed that, I mean, we followed the CO2 reduction reaction mechanism through different reaction pathways. So you could easily, even using this small particle, very small particle, you could easily have CC coupling and then generate some product. You see, it's even downhill. Like when you have a COH as intermediate, coupling COH coupling is quite downhill and it happens easily. You can have it. And then you can further protonate it and achieve a CC, for example, which is the barrier is not really large. But then, even if you have this CC or start with CO and then the CO coupling or CH2 coupling happens, you get ethylene. So producing ethylene, in fact, is easy. And you can have it even on this small particle. But then what happens is that the ethylene sticks there and doesn't really leave the surface because it is strongly absorbed to the surface because of the shape of the surface, perhaps. I assume these particles are very low coordinated. So there are more electron density around them, so they can create a stronger chemical bond. And this is what we observe from the, let's say, charge localization and charge distribution through the DFT again. So once the ethylene remains there, then you give it the possibility to further be protonated. So it can be further protonated here, and you see there is almost no energy barrier. And then even further until you get ethane. But then this ethane can be easily converted to methane and produces. So then what you have, you can reach CH and then produce CH2 here. I mean, this is just for the sake, I couldn't really put them under each other for the presentation, so I just break it down. So after this step, you bring it to another hydrogenation, you produce CH2. So the CH2 is the key in our experiment, and you see it also in our Raman result. But then CH2 can either produce methane for you, or can easily produce ethylene. Both of them are green pathways. That means it's downhill. But the problem with ethylene is that it gets converted back to the methane again. So we said that even if you produce ethylene through using these small particles, even in alkaline electrolyte, which favors basically the CC coupling, then eventually, because it's there, it remains and it doesn't leave the surface, it will be converted again back to the methane. And that's why we produce larger methane. This is again, our hypothesis. And we try to support the hypothesis through different experiments, such as looking into the ethane desorption, or through the Raman spectroscopy, what happens to the CC coupling, or what's the CH2 population on the surface, which we're supporting. And eventually you see the trend here that the small particle doesn't really produce ethylene, most likely because of that is converted to the methane. I hope I answered your question, but again, this is only one angle to the problem. There might be a lot of reasons, like a low coordination, or the shape even, or not having, as the Professor Zhicheng mentioned, not having enough surface coverage of CO, because it's very small particle. You don't have so many CO there to let them to couple even. So these can be the reason for not producing ethylene at very small particle size.
Thank you for your answer. So you mean for the small particles, even the carbon-carbon coupling is happened, it will also dissociated into the methane.
In fact, you have coupling, and then you have decoupling here. This is step. So it's kind of a loop happens here. You have the coupling, but if you have the coupling, then decoupling also happens, and then you produce again methane. So also very interesting phenomenon for ourselves. I guess in the future we need to further investigate that and provide more support for it.
What factor is to dominate this effect? I mean, is the facet or the size of the nanoparticles?
So our study is just focused on copper. So I don't know if we do the same thing with other particles, let's say silver or palladium or I don't know, the lead, if we get the same kind of observation or not. But for copper, I guess the both parameters that you mentioned could be important. One is the facet. The other one is the particle size. For the facet, we don't have any brilliant idea how we can have a small particle with other facets. Let's say one way to examine which one is important, the particle size or the facet, is, for example, synthesizing particles with very small size, but then with different facets. For example, this was my question always for my PhD student. I was telling him that, okay, can you synthesize the same particle with the same size, but with 100 facet? Then if we are able to synthesize that particle, and then we run the same experiment, then if we observe again a lot of methane, no ethylene, then we will conclude that the particle size is important, not the facet. But unfortunately, we are not able to synthesize it. At least from the DFT perspective, we showed that this particle 111 is more stable than 100. Here, because you can have a cube, a very 100 cube, very small, but we show that it's not stable. At that size, it's not stable. When it gets larger, yes, you see that the cube is more possible because the excess energy is lower, so it gets more stable. But at very small particle size, we couldn't get a stable 100 facet. So at the moment, I cannot be kind of assured that facet is important or particle size. I say both of them are important. They are related to each other.
Okay. Thank you. Yeah,
Thanks
again for your wonderful talk.
Yes.
Hi, Annie. Yeah, can you hear me?
Yes.
So now the number of audience reach up to more than 6,800. So many for the question and answer session. So also our staff have collected some questions from the audience. Just you mentioned, what about the copper-based alloy small nanoparticles? What's the trends?
What's
Yeah, copper-based alloy small nanoparticles with different size. They mentioned for example.
Copper-based alloys.
Yeah. This is one question.
That's a very interesting question. It's what we are doing right now. I mean, we have not tested them yet. I can tell your audience that we are trying. First of all, we are running similar DFT computations, and this is kind of a high throughput DFT computation, which because the number of computation is a lot, more than like a couple of thousand computations, although simple, but a lot of computation. So first of all, we started working with silver and tin because copper is for hydrocarbons, multi-carbon products. Silver is representing catalyst for CO, and then tin represents catalyst for formate. So we try to cover all of them. So we are running the similar computation for these pure metal, and then the next step for us is creating the alloy. Still, I don't have any answer for that, but hopefully in the near future we can get the answer for this to see what happens if you have alloy. Let's say a copper, silver, but very small particle. We have the experimental facility to run this test, But from DFT competition, we are still waiting for the results. Unfortunately, I'm not able to say anything about what we should expect.
Okay, thank you. Thanks for your reply. Another question from the audience. Mentioned, let me see. I think he or she means control the temperature can tune the selectivity towards C2 products. Maybe I think maybe page, let me see. Yeah, last page, previous page, 14 or 16 or 13 you mentioned. Oh yeah, I think this one.
13 and 14,
yeah,
we talked about the temperature.
Yeah. He or she wants to know the reason why.
So the reason is in this slide, we said we probably can expect observing some sort of ethane, not ethylene, because for the ethylene, for the desorption, we need 1 electron volt. And 1 electron volt is almost 100, if I'm not wrong, in terms of the conversion, like 100 joule per mole, but then which is not easily surmountable at room temperature. But 0.25 is something that at room temperature you can overcome. Then we said this step is not electrochemical step. You know, this is not proton transfer step. This is not electron transfer step. It's just the desorption, which is merely a thermal phenomenon happening, a thermal kind of desorption. So if you increase the temperature, what happens? You would help the ethylene, which is absorbed on the surface, leave the surface easier. So at higher temperature, you know that the absorption decreases, so the efficiency for absorption decreases, and then the desorption becomes easier. So we said if ethylene is in fact on the surface, by increasing the temperature, we should observe more ethylene, and that's why we ran this test. So this is the background. So you see in our CO2 gas, there is no impurity like ethane impurity. So this is the GC results. And this is the time that we expect the peak for the ethane. So at room temperature, that's the peak that we get for the ethane. So the amount of the ethane is very small. We can't even convert it to the Faraday efficiency because it's very small, like less than even 0.1%. But then that's a peak. It shows that we have ethane in fact. But then we increase the temperature to 80 degrees. So we expected that we should observe more ethane, and we observed that. So it's kind of supporting the idea that the ethane is absorbed there, and by increasing the temperature, you can help it to be dissolved. But we did the same experiment with large particles. There was no ethane neither at room temperature nor at higher temperature. So that means on larger particles such as 100 nanometer or 200 nanometer, there was no such mechanism that the ethane is absorbed on the surface. So we didn't have that procedure. In fact, once the ethylene is produced, it just leaves the surface on large particles. So there's no chance for having the ethane. I hope I answered the question.
Okay, thank you. Thanks for your reply. So I have one question. Yeah. So very interesting work. Just like you also mentioned, Professor, you also mentioned, especially for C1 products, first the CC coupling will happen, and then decoupling will happen. So can we do in situ IR or Llama to identify this process or monitor this process, especially with time? We can. Yeah.
So first of all, I need to clarify that no, not necessarily coupling happens and then decoupling. You can go from C to CH and then CH2, CH3, and then methane. So methane can also be produced through just a single carbon hydrogenation. So that's not the coupling is not the pathway. But we say once you have CH2, you may go downhill to produce methane, but you can also have the coupling. It's possible. We say that. But then we say if the coupling happens, then eventually you have some sort of decoupling from ethane to produce again methyl adsorb on the surface, and methane dissolve and goes to the gas phase. So this is just clarification. And then our IR, we didn't run the time resolved kind of Raman or IR. We didn't have that sensitive IR in our lab, but we performed Raman with different I mean, by how we call it, I forgot the terminology. Sorry about that. Instead of using the KOH, we use the KOD, the marked hydrogen to show the shift to ensure that the carbon products is in fact coming from the CO2, not coming from any other sources. So we were able to observe the CH bonding, the CH vibration, and also we observed the CC adsorb on the surface. So on nano, like very small nanoparticles, we observed a higher population of the CH bond, and as you see them here, and CC bond. But on large particles, we didn't observe those features, which was kind of supporting the idea that if you have a small particle, these species should remain on the surface. But again, to answer the time resolve question, no, we didn't have the facility to run it, but that's also interesting question.
Yes, thank you. If you can do time dissolve, very interesting to first company and then the company. This phenomenon, this very interesting. Yeah, if in this way.
Yeah, no, I take note. I take note for that, and I look forward around in my colleagues' lab to see if they have the facility. But you're right. That's very interesting phenomenon.
Yeah, yes. Thank you. Let's see the paper mention this process, two processes. Thank you. So already, let me check. More than 1 hour, close to 1 hour and 1.5 hours for your talk. Maybe so late for you. Thanks again for your wonderful talk and detailed response to all questions. And also welcome to submit your work to SmartMat. When you're available in future, welcome to visit China, Tianjin University. Welcome. Thank you.
Thank you so much. It was a great pleasure for me to be here with you, and thanks for the questions. I'm so looking forward to visit your university, and definitely I will keep the SmartMat in top of my list for our upcoming works. And I would encourage my students to consider your journal for their publications for sure.
Okay, thank you. Thanks for your strong support of SmartMat and to this webinar. Thank you. Okay, bye.
Have a good day there.
Bye. Yeah, bye.